Alright, so what we have here is a new set of reactions that's going to have a common theme to it. And the common theme is, what if the XY pair that's being attacked, the reagent over the arrow, has a lone pair on the X atom? And so specifically what I'm referring to is in the previous videos where you have an XY pair that's not immediately apparent as to what the electrophile is or what the nucleophile is, but that some part of that can at least be delta plus and therefore electrophilic, while the other part is delta minus, nucleophilic. And so then what happens is your double bond comes in and attacks the electrophilic part, which then liberates the nucleophile. You end up adding the electrophile to one half of your double bond, and then the nucleophile wraps around and adds to the carbocation. So that's what we're talking about here. And now the change is, what happens if the X group, what happens if the electrophile itself, even though it's electrophilic, has a lone pair on it? How does that change what happens next? And where this comes from is looking at Br. And at first, again, it's not obvious what you're looking at. It's not clear how that fits into this picture, but let's redraw the bromine as a slightly electrophilic bromine bound to a more nucleophilic bromine. Now, does that sound a little silly? Yes, it does, but you have a relatively large molecule, and it can, for whatever reason, become polarized briefly, just arbitrarily, momentarily, and one end of your Br bond is going to be delta plus, and that could be what causes the mechanism I've just described to take place. So the Br could be attacked by the double bond, kicking out the other Br as Br minus. So in other words, though this should be neutral and not particularly polar in the first place, it can become polarized, and one side could end up as delta plus, and then that could then be attacked and then kick out the nucleophile. But not pictured on this bromine at the moment is, of course, another 3 lone pairs. So even though you could attack it because it's delta plus, it has on it some electron density. And so the intermediate I draw immediately after this set of attacks happens looks like this. Now we have a cationic species because, of course, the double bond made a bond, and one side or the other of the double bond did the attacking, and a plus is left on the other side. So that's what we form immediately. And then, of course, we have the Br minus floating off. And so though this Br minus is going to be attracted to that plus and will eventually bind to it, it's further away than this Br that's just right there. And Br is huge, by the way, relative to the carbon atoms. And so what it's able to do is essentially donate its electron density immediately back into that orbital. And so what you end up drawing is now something that's going to look a little bit silly, but is nevertheless the thing that forms first. And it forms instantaneously. It does not, in fact, form a carbocation first. I'm just using that to illustrate what's going on. This is, in fact, the intermediate that gets formed in the immediate short term. So again, this is a thought experiment. This is not, in fact, what happens. What happens is the Br that's getting attacked just simply attacks back simultaneously. And so rather than having this little offshoot, which again was just a thought experiment, the set of arrows you draw initially looks something more like this. This attacks kicking off the Br, but at the same time the lone pair kicks back on. And so the first actual intermediate of the reaction looks like this. And what you have is the bromine at the moment either sitting on top of the double bond or sitting behind one or the other, because this was arbitrary. It could have come from the top or from the bottom, either way. But those two bonds have to be the same, either both wedges or both hashes. And of course you've got the Br minus floating around nearby, and so that Br minus could then attack from either side, by which I mean either the top or the bottom carbon, but it needs to attack from behind the bromine. So since the bromine is toward the camera, the other bromide would have to come in from behind. The end result is going to be explicitly one bromine up and one bromine down. So the way you arrive at this particular final product is if this bromine had attacked from behind at this position up here, which then causes the bromine to end up toward the camera on the bottom. So this attacked the top carbon, leaving the bromine toward the camera. Alternatively, of course, you make the other enantiomer, the other product, and what that will have is bromine toward the camera on the higher carbon and bromine away from the camera on the bottom. And so what happens here is the initial attack of the bromine on the double bond is going to be arbitrary, either the top or bottom. But then explicitly, the second bromine attack has to come from behind. So this is kind of an SN2-like process, even though this is not looking like an actual SN2 reaction. So what I've drawn so far is just the bromine doing the attack, but to arrive at this top, this arrow comes in, causing this bond to break and leading to that product. Alternatively, this arrow could come in from the bottom, causing that bond to break, leading to that product. attacked. I want to focus your attention on what the initial attack looked like for this. What you have is a double bond, and the bromine is just kind of sitting on top. And so then this pair of electrons went and attacked the bromine. The pair of electrons that's facing toward that comes back in and makes the bromonium species, this little triangle-looking thing with the bromine charge, and that causes the other bromine to leave as Br minus. And what that forms, again, in the short term, is going to be something that looks like that. But it's not actually sitting there directly bound in the way that you think when you look at it. The bromine is rather more loosely bound than you would have the impression of when you're looking at this. And though there's a plus explicitly on the bromine, that's a little bit misleading. Where the plus actually is located is on the carbons nearby. So even though there's a plus on the bromine, where you're going to attack is on the carbons that the bromine is attached to instead. Down here, what I'm illustrating is the same sort of mechanism on a slightly different product. And so the way you want to think about this molecule is that you have a mercury atom, which is going to be relatively electrophilic. It is, after all, a metal, and it has a bit of charge on it. And it has a lone pair on it as well. It's got a pair of electrons. But you also have two ligands on it, and these ligands are the acetates. And they don't really participate in the reaction. They're not really doing much of anything at all. But again, what happens here is when the double bond attacks, that will cause one of the ligands to leave, but the pair of electrons will go and join back in. And what that will do is form a intermediate that looks like this. And this time I have arbitrarily chosen the mercury to attack from the bottom so that you now have hashes, two hashes to the mercury. And once again, this is going to be a scenario in which the mercury is itself positively charged, but you should not imagine that the mercury acts as though it's positively charged. Instead, the effect of having a plus right there is that these two carbons act as though they are positively charged. Then, of course, what happens next is that you have a water molecule floating around nearby, because that is the solvent in which we are running the reaction, and the water can come by and displace the mercury in what would appear to be an SN2-like fashion, although it's really not. It's really more like a SN1 type fashion, and I'll explain what I mean about that in an upcoming video. But after doing the necessary proton transfers, what you end up making is water adding on the one side and a mercury bond, carbon-mercury bond on the other side. Now, this is a horribly toxic material. You wouldn't want to try to isolate this. It could do very bad things to you and so on, and it's not particularly stable. So in any event, we don't let that sit for very long. But this is kind of the black box thing that happens on the way to what we actually isolate. So if you run this kind of oxymercuration reaction in order to add water across the double bond, you're never really going to stop at the mercury. You're never going to isolate the mercury. Instead, you take this material and immediately throw in sodium borohydride, which will reduce it. And the way that this particular mechanism goes is formally magic. We're not really going to talk about how it goes because it's not the point. Instead, what happens is you kind of do the equivalent of taking an H- and replacing the mercury. So in other words, your final product here is going to be like this, because where the mercury was gets replaced by an H. So it's kind of like you added H- to replace that bond. And again, in this case, since all the other hydrogens are not drawn, I would erase it, and the final product here is just that. So it's the equivalent of adding water across the double bond, but you do so by using mercury first, and then sodium borohydride in the second step. And again, the reason why I'm illustrating this for you right now is because it makes the same kind of intermediate in both cases. And again, the core idea here is, what if the XY pair that gets attacked, the thing over the arrow that gets attacked, has a lone pair on the thing that gets attacked? Well, then you never actually form a carbocation. Instead, you go directly to this kind of triangle-shaped intermediate where you have a bromonium, a bromine with a plus on it, which has the effect of making these two carbons more plus, or, same idea, mercury with a plus on it, which again has the effect of making those two carbons plus, even though formally we're drawing the plus on the mercury itself.